So, good morning. Hello, good evening. Uh, so today I am going to discuss multicollinearity. We know, suppose this is the model Y curve. There are n observations. X is the coefficient matrix n cross k. K is the number of regressions. Beta curve. Regression coefficient vectors. Error. Vector of error component. Okay. So the basic assumptions for this model is rank of X should be K, that is number of explanatory variable. This means all explanatory variables are independent. That is, there is no linear relationship among the explanatory variables. So this termed as the explanatory variable are orthogonal. But in many situations, rank of X may be less than K. That is, the explanatory variable may not be independent. the situation where the explanatory variables are highly intercorrelated is referred as multicollinearity. So that means when rank of x less than k, this implies the explanatory variable are not independent. They are not orthogonal. That means there is a correlation. So this situation is called multicollinearity. Okay. So the source of multicollinearity is due to following fact. One, method of data collection. It is expected that the data is collected over the whole cross-section variable cross-section of variables. It may happen that the data is collected over subspace of it may happen that the data is collected over a subspace of the explanatory variable where the variables are linearly dependent. For example, sampling is done only over a limit of over a limited range of explanatory variable in the population. Next, this may occur multicollinearity may occur due to model and population constraint. there may be exist there may exist some constraints on the model or on the population from where the sample is drawn. The sample may be generated from that part of population having linear combination another reason is existence of identities or definitional relationship. There may exist some relationship relationships among the variables and this may be or which may be due to which may be due to sorry the definition of variables or any identity relationship among them. For example, if data is collected on variables like income, saving, and expenditure. Then we know income equal to saving plus expenditure. Such relationship will not change even when sample size is increased. What sample size increases. Next reason is impressive formulation of model or impressed formulation of model. The formulation of model of the model may unnecessarily be complicated. May unnecessarily be complicated. For example, the quadratic or polynomial terms or cross product term or cross product terms may appear as explanatory variable variables. For example, suppose x1, x2, x3 are three explanatory variables, and if we add, and suppose we add cross product term x1, x2, x2, x3 and x1, x3, then now the number of explanatory variables are is explanatory variables is 3 plus 3, that is 6. So here the k, which which is denoted by number of explanatory variables, rises to 6, and the next reason is for the source of multicollinearity. Over-determined model. Sometime due to over-enthusiasm, sometime due to over-enthusiasm, large number of variables are included in the model to make it more realistic, and consequently number of observation n should be less than k, where k is a number of explanatory variables. Such situation can arise in medical research where the number of patient may be small, but information is collected on a large number of explanatory variables. Another example, if there is time series data for 50 years of on consumptions data, 50 years of consumptions pattern, then it is expected that the consumptions pattern does not remain same for 50 years. So better option is to choose smaller number of variables, and hence it results in less than k. So these are the source or sources. These are the sources of multicollinearity. Now I am going to discuss the consequences of multicollinearity. If multicollinearity happen, then what is the consequence? So this is over determined model. Consequences of multicollinearity. Suppose I consider only two explanatory variables, then the model is y equal to beta 1 x1, beta 2 x2. Here I ignore the intercept term. And this y here, this y is standardized form of observations vector, that is small y. I denote this by small y. The small y equal to capital Y, which is the original observation, minus expectation mean, sample mean of the observations. It is better to write in that way. Capital Y minus y bar by sy. Sy is a sample standard deviation. Similarly, x1 is capital X1 minus x1 bar by s1. S1 is a standard deviation, samples standard deviation of corresponding the explanatory variable x1. x2 is a x2 minus x2 bar s2, and epsilon is a error term where expectation of epsilon equal to 0 and variance of epsilon equal to sigma square I. You can use card. So this should be, this is simply it is better to write in that way. This is the original model, okay? yi equal to beta 1 star, say, x1 I beta 2 star x2 I plus epsilon I, okay? Epsilon I star. Now I transform this to small yi. Small yi is capital Yi minus capital Y bar by sy. Then this is beta 1. Beta 1 is not same as beta 1 star. Is this is x1 I star. This is x1 small x1 I plus beta 2 x2 I plus epsilon I, where x1 I is capital X1 I minus x1 bar by small s1, which is a sample SD of x1, small x2 I, this is equal to capital X2 I minus x2 bar by small s2, which is a sample SD of x2. Then if you look at this model, suppose I have an observation. In matrix notation, I can write this as y curl equal to beta 1 x1 curl, beta 2 x2 curl, epsilon curl, where epsilon curl is expectation of epsilon curl is 0 curl and dispersion of epsilon curl is sigma square in. Now the x prime x is x1 curl prime x1 curl, x1 curl prime x2 curl, x1 curl prime x2 curl, x2 curl prime x2 curl. So here x is first column vector is x1 curl, second column vector is x2 curl. Okay, so this should be 1. This is R is a correlation coefficient between x1, x2, rather it is better to write capital X1, x2, this should be R1. So OLS estimator of beta curl hat, beta curl, which is denoted by beta curl hat, beta 1 hat, beta 2 hat, this is equal to x prime x inverse x prime y, small y curl. Now x prime y curl, this is equal to x1 prime y curl, x2 prime y curl. So this is again ry1 and this is ry2, where ryi is a sample correlation coefficient between xi, capital Xi, and y, I from 1 to 2. So x prime x inverse is equal to 1 by 1 minus r square, 1 minus r1 ry1 ry2. So beta 1 curl hat, which is equal to y1 minus r y2 by 1 minus r square, and beta 2 hat, this is equal to r y2 minus r ry1 1 minus r square. Now if r, that is correlation between x1 x2 tending to either plus 1 or minus 1, then variance of beta 1 hat, which is, we know, variance of beta curl hat equal to x prime x inverse sigma square, and here it is. If you look at this portion into sigma square, then we see that variance of beta 1 hat equal to variance of beta 2 hat, which is equal to sigma square by 1 minus r square. So if r equal to plus minus 1, then variance of beta 1 hat and equal to variance of beta 2 hat, this tending to infinity. So we can conclude that, so if variable, so if variables, explanatory variables, are perfectly collinear, the variance of OLS becomes large. This indicates highly unreliable estimates, and this is an inadmissible situation. Note that r equal to plus minus 1, that means perfectly linear, when x1 x2 are perfectly linear, then this imply x prime x, if you look at this, that is here 1 plus minus 1 plus minus 1 1. For example, if you take r equal to plus 1, sorry, then x prime x is equal to 1 1 1. That means rank of sorry, rank of x prime x equal to rank of x, which is equal to 1, which is less than 2. Here 2, here number of explanatory variables is 2. And when, similarly, when r equal to minus 1, then x prime x, this is equal to 1 minus 1 minus 1 1. Again, here also rank of x equal to 1, which is less than 2. So note that if r is close to 0, then multicollinearity does not harm. And it is termed as non-harmful multicollinearity. If r is close to 0, then multicollinearity close to plus minus 1, not 0, okay, close to plus minus 1, then multicollinearity implies the variance and it rises very good. This is termed as harmful multicollinearity. So, have you any question? Please tell me. If no, then I wrap this portion. Have you any question? If you have any question, please tell me. Otherwise, I wrap this portion. Hello. Hello. Next point, there is no clear cut boundary to distinguish between the harmful and non-harmful multicollinearity. Generally, if R is low, the multicollinearity is considered as non-harmful, and if R is high, the multicollinearity is considered as harmful. Now, if high multicollinearity occur, that is in case of near or high multicollinearity, following consequences are occurred. OLS estimator remains unbiased, but variance of variance become variance of OLS estimator becomes very large, which we already seen. Next, and this means as OLS estimator becomes impress become imprecise, become improper or imprecise, or OLS estimator not work well. Secondly, due to, suppose you want to test, this is the null hypothesis, beta 1 equal to 0, and we use a t-test, which is the b1 is a OLS estimator, OLS estimate of beta 1, and this is the estimate of variance of b1. Since if multicollinearity occur, then variance of b1, this is large, and this implies b1 by had b1, this is small, and as a result we always we always better to say not always, h naught is accepted, or h naught is more oftenly accepted, and as hence harmful multicollinearity intends to delete important variables. So be careful. Similarly, if since this is very large, v variance of estimate of the variance b1 is very large, if multicollinearities occur, this imply the confidence interval (100 into 1 minus alpha percent) confidence interval of beta 1, that is b1 minus t alpha by 2 n minus 2 n minus 1 n minus 2s, it is better to say if you ignore the intercept term, then it is n minus 1. And suppose if you consider only two explanatory variables, then this is n minus 2. If you ignore the intercept term, then this should be, or rather you can write it generally, that is n minus k. Suppose k is number of explanatory variables, and if you ignore the intercept term, okay. So if this thing is large, so the interval, this imply the confidence interval becomes wider. And last point, the OLS estimator may be sensitive to small changes in the value of explanatory variable, in the values of explanatory variables, if some observation are added or dropped, OLS estimator may change considerable considerably in magnitude as well as in sign. Ideally, OLS estimator should not change with inclusion or deletion of variables. Thus, OLS loses stability and robustness. So, OLS loses stability and robustness. Now, consider the model Y. This is the standardized form, that means the variance of y is 1, that is variance of y is standardized form means actually not 1, actually I want to say this is the transform form standard, that is y minus unit length, actually y minus y bar by small y by sy, and beta 1 beta I, this is I from 1 to k, capital xi minus x bar capital xi minus xi bar, actually, okay, and si plus epsilon. So I denote this by beta I capital xi plus epsilon I. So therefore x prime x, where x is, so if you write this in matrix notation, y curl plus x beta curl plus epsilon curl, where x is x1 x2 xk, then x prime x gives the correlation matrix R, and I denote R inverse by capital C matrix, which is here it x prime x inverse ij, the Cij, ijth element of matrix C, then the jth diagonal element of matrix C is Cjj, which is equal to 1 minus Rj square, where Rj square equal to coefficient of determination from the regression of xj on the remaining k minus 1 explanatory variables. Now, if xj is highly correlated with any subset of other k minus 1 explanatory variables, then Rj square is high and close to 1, and consequently variance of jth OLS estimator, which is Vj is equal to Cjj sigma square, and this is equal to sigma square by Rj square, and since Rj is close to 1, this means this is tending to infinity. So the covariance between beta bi and bj will also, these are the estimator of beta j and beta I and beta j respectively, will also be large if xi and xj are involved in the linear relationship leading to multicollinearity. Now the least square estimates beta j bj of beta j become too large in absolute value in the presence of multicollinearity. For example, L square, which is defined as a square distance between b and beta, then this is beta b curl and beta curl. B curl, beta curl prime, b curl, beta curl. Then expectation of L square, which is, we write this as j from 1 to k bi beta I square, I j from 1 to k expectation bi sorry bj beta j square. So this is variance of bj, and which is equal to sigma square trace of x prime x inverse. Now we know the trace of a matrix is equal to sum of the eigenvalues, and if lambda 1, lambda 2, lambda k are the eigenvalues of x prime x, then eigenvalues of x prime x inverse is 1 by lambda 1, 1 by lambda 2, 1 by lambda k. So this is equal to sigma square I from j from 1 to k 1 by lambda j. And if x prime x is not full rank, or if x prime x is ill conditioned, that is due to the presence of multicollinearity, then at least one of the eigenvalue will be small. So the reciprocal of this eigenvalue is very large. As a result, the distance between b and beta may also be large. Thus, expectation L square, which is sigma square trace of x prime x inverse, or if you look at this portion, then this is x prime expectation b prime b to b prime beta plus beta curl prime beta curl. So if you simplify these two portions, then you get expectation of b curl prime b curl equal to sigma square trace of x prime x inverse plus beta curl prime beta curl. So this means b curl is generally, because this is very large, so b curl is generally longer than beta curl, and this means OLS estimator are too large in the absolute value. Hence, we can conclude that the least square procedure bad estimates, least square procedure produce bad estimate bad estimates of the parameters in the presence of multiclonal. This does not imply that the fitted model produces bad predictions also. If the predictions are confined to X space with non-harm non-harmful multicollinearity, then predictions are satisfactory. So here I want to stop today. In next class, I will discuss multicollinearity diagnostics. So have you any question? Please tell me. If you have any question, please write in the comment section. So in the next class, we will discuss multicollinearity diagnostics. On Thursday at 6 p.m. So have you any question? If not, then I will end this stream. Please tell me. So I think if you have, so please tell me, have you any question? Okay, thank you. We will meet again on Thursday at 6 p.m. We will discuss multicollinearity diagnostics that day. Okay.